Okay, guys, one other thing that we can deal with when we're thinking about dimensional analysis is something called percent yield, and this would be getting into the lab and figuring out, did you make as much as you could? So just to present this, if we had 24 pancakes that could be made, and we're going back to our pancake making example, but let's say 3 of them were burnt and 1 of them fell on the floor. The question is, how many pancakes did we actually make? So what we could do, we realized we could make 24, but we lost 4 of them, right? If everything went okay, so we say 24 is the theoretical yield, right? Everything went perfectly, but 4 were lost. So that means we had a 20 was an actual yield, right? When we went into the lab, the amount that we actually made. Lab, kitchen, same thing. So to bring this to chemistry, the theoretical yield is the amount that is calculated, right? So when you come up here on our last problem with the limiting reactant, how much of each substance, we calculated that we could make 3.33 grams of our product of the silicon nitride. That is in theory if all of the 2.00 grams of silicon reacted. Sometimes it doesn't all react. So this calculated amount using the stoichiometry, using the mole-to-mole ratio and the molar masses, that is known as your theoretical yield. The actual yield is the lab data. Like, we went into the lab and we did the procedure, and this is the mass that we measured. And those two things are usually not the same. They could be close to each other, and the closer they are, the better you were at your lab. Or even if they were bad, there could have been a systematic error, whatever, but they are usually not the same. So if you want to calculate your percent yield, it is how much you got over how much you could have gotten times 100. So if we wanted to calculate the percent yield of pancakes, well, our actual yield was 20, and our theoretical was 24. And again, we're going to put this out of 100. This would give us an 83.3% yield of pancakes. Because again, what am I yielding? What substance am I yielding? Because we might have more than one product. Okay. So when we're bringing this to chemistry examples, we need to, in general, calculate the theoretical yield and compare it to our actual yield. So if we know that we're doing stoichiometry, we need a balanced equation. So in this example, when copper 2 sulfate reacts with zinc, copper and zinc sulfate are produced. So we need to write a chemical equation. Copper 2 sulfate reacts with zinc, and we form copper and zinc sulfate. Remember that zinc is always +2. And looking at this reaction, it is balanced. How nice. We don't need to do any coefficient balancing. That is not always the case, but in this case it is. So it says, upon reacting 1.274 grams of copper sulfate with zinc, this is the amount of copper that was obtained, and we want to know the percent yield. So just like we did in class today, we kind of want to, we want to set up ourselves and figure out, in order to answer the question, what do I need? So if I want to find percent yield, first of all, we need to figure out what we're yielding, right? Since they gave us a mass of copper, that's product. So that's the yield that I'm interested in. So we are interested in the percent yield of copper. So that means that we need to, we need to find the theoretical, if I can spell, theoretical yield of the copper, and put it over the actual, or the lab yield of copper, and multiply by 100. Okay, so we have one of the masses from in the problem, and we can assume that is our actual yield, right? It was obtained, it was done in the lab, it's an action-y verb. So we can put the 0.392 grams of copper on the bottom. And we want to know, oh, I have these mixed up. Ugh. Sorry, friends. Switch those, please, because it should be actual over theoretical. So 0.392 grams of copper. So what I need to plug in over here is the theoretical yield of copper, which comes from stoichiometry. And that is where our other number comes into play. So we reacted 1.27 grams of the copper sulfate, and we obtained 0.392 grams in the lab. So if all of this 1.27 grams of copper sulfate reacted, how much copper could we have made? So here we're going to do our 3 steps of stoichiometry, where we're going to turn our grams of copper sulfate into moles of copper sulfate and use our mole-to-mole ratio from the balanced equation, which these are all 1-to-1. And again, I'm interested in the theoretical yield of copper, so I'm going to turn this into copper. And for every 1 mole, turn the moles of copper into grams of copper. So we got 63.55. And again, I'm rounding this to 2 places out of decimal, even though I could go 3 because it technically has more sig figs than the 1.27. But if this value of copper sulfate had more sig figs, I would probably keep as many as I could. You don't want your molar masses to be what limits you in your significant figures. So then to get the molar mass of copper sulfate and sulfur 32.07, I get 159.62. So if all of the copper sulfate were to have reacted properly, we would have been able to obtain 3 sig figs. Can actually keep a little bit more because this isn't our final answer, but we can track our significant figures to the 3rd place. So if all of the copper if all of the copper sulfate were to have reacted completely with no error, we could have gotten 0.50563 grams of copper, but we only got 0.392. So this, we're going to have a less than 100% yield, which is normally the case. Sometimes you can get over. We'll talk about that later. But 0.392 divided by 0.50563, we got a 77.5% yield of copper. Okay, so we're just adding to our understanding of this dimensional analysis and realizing that we don't always get a 100%